Good evening, everybody. My name is Stavros Nikolopoulos. I'm the director of Nanomegas, based in Belgium. I have the pleasure to chair, together with Dr. Tarun Sharda from Techno Instruments, the today webinar based on advanced characterization techniques in TM by precession electron diffraction. I will just only take a few minutes. I would like to present our company, Nanomegas, that work together with TechnoS in India. So Nanomegas is a company that presents solutions in electron diffraction, in transmission electron microscopy. We are about 15 people. We're based in Brussels, Belgium. We have our own research and development facility in Brussels with our own microscope, and we are collaborating in several research projects. In concrete, STEAM3 is one of the most relevant. That is a network of leading microscopy laboratories all over Europe. So today we have two distinguished speakers. One is Professor Gosal from DMRL and Dr. Partha Gosal from our application specialist. We'll speak about different aspects of diffraction devices, diffraction-based devices. One is the A-star, that is the orientation of phase mapping in a TM. We have a long history about this important application with more than 160 units worldwide, already 5 installed in India, where we can do orientation of phase mapping in nanometer scale in a transmission microscope. The technique has been developed more than 10 years now, and has been very successful through the microscopy community. We have more than 600 papers so far published on this technique and is ever going. So after the talks, if you want to see more about our techniques, you can visit the website of nanomegas.com, where in bibliography section, you can see in very much detail applications in every field about orientation phase mapping, from semiconductors to nanostructures, minerals, and so on. So important thing to say is that the A-star orientation phase map technique that Dr. Gosal will also speak about this today can be interfaced in any transmission microscopes, yes, corrected or not, modern or less modern, and with a series of important detectors and direct detection cameras. Also, Dr. Partha Das will speak about two other exciting techniques. One is electron diffraction tomography, or micro-ED, as some of us know, and the electron pair distribution function that has a lot of applications to characterize amorphous and nanocrystalline materials. So this is the two scientists that will make presentation. As I said before, Professor Partha Gosal is head of electron microscopy laboratory of DMRL in Hyderabad, India, and Dr. Partha Das, that is our application specialist based in Spain. Before we start, I would like to say a few instructions. So just after the talk, so just after 1 hour, there will be a question and answer session. Then you can type your questions in the chat box that you see on the right, top on the right. So you can type any question you like, and then the chairman will ask those questions to the two speakers, and the speakers, they can answer those questions. So please write. We'd like you to write the names and your question. So usually, if there, depending on the number of questions, but normally we'll answer in the order we have received the questions. And then if there are too many questions, we ask all of them, but probably some of them by email after the webinar. So thank you very much for your attention. I give now the talk to Dr. Partha Das. So, Partha, you can start.
Hi. Can you switch off the microphone because otherwise there are a lot of noise of the keyboards and others are coming. So, okay. Hello, everyone. Good evening because it's afternoon here in Europe, but it's almost evening in India. So I am Partha Pratim Das, application specialist in nanomegas. Thanks, Stavros, for the introductions, and thanks everyone again for joining the webinar on structural characterizations in TM by 3D on electron pair distribution function. There will be two parts of the presentation. First part is on 3D electron diffraction, and second part is on electron pair distribution function. I started my scientific journey with X-ray diffraction, and for last few years I have been working on electron microscopy based diffraction techniques. In these presentations I will show some of our work and also a journey of many other scientists in this field of electron diffraction. As I said, there are two parts of the presentation. First part on electron diffraction, 3D electron diffraction, and second part will be electron pair distribution function. PED experienced a true rebirth in 1976, actually, thanks to the research of American scientist Douglas Dodson. What information one can really obtain using 3D electron diffraction? Let me show you an example from our most recent work. Once there is a crystal, one can acquire 3D electron diffraction data. And from the 3D electron diffraction data, one can determine the unit cell, symmetry, and extract intensities. And then one can find all the atomic positions present in the structure from the extracted intensities, as you can see in this slide. There are different methods for extracting structural information from a crystalline material. Most common method is X-ray diffraction. But with single crystal X-ray diffraction, one needs 1 micrometer crystals or larger. For powder diffraction, though the crystal size requirement is small, but there are more than one phases present in the material, extracting structural information is really challenging. Other possible method to extract structural information is by X-ray femtosecond crystallography or free electron laser. But each of these above-mentioned methods have its own challenges. When facing such a problem, the method of choice could be 3D electron diffraction in electron microscope. Because if there is more than one phase present in the sample, it will not be an issue anymore, as we can study single nanometer size crystals in electron microscope. In TM, we can also perform spectroscopic and chemical analysis technique at the same time, which is of a great benefit. Now let me show you an example from a recent publication to better understand what size of crystal can actually be used in TM. As you can see in the magnified image of the crystal, the purple colored circle area is required for collecting X-ray data from a microfocus beamline. And on the top, you can see the yellow dot, which shows size of the crystal used for 3D electron diffraction. Hence, it shows we only need a very small size of a crystal for 3D electron diffraction study. Now, what are the major differences between X-ray and electron diffraction? As you can see, for the electron diffraction, UV sphere is flat in comparison to X-ray because of the very short wavelength used in electron diffraction. That means one can collect sections of the reciprocal space just from a single shot. Also, we know once the crystal size becomes smaller, the diffraction patterns becomes broader. As you can see in the example later, the diffraction pattern is extremely broad. This is known as X-ray amorphous, but this size of crystal one can study in TM to obtain structural information. In case of electron diffraction, the interactions of the beam with crystals is extremely strong, and that makes the diffraction patterns non-kinematical, or we call it dynamical. which precisely means the intensity modulations in the diffraction patterns get messed up, and additionally, one can see more spots which should be absent due to systematic absences. There is a technique to minimize the dynamical scattering or dynamical diffraction in electron diffraction experiment by using a technique or a method termed as precession. The method was first proposed by Vincent and Nicolay in 1994. I'll show you later what precession technique actually means. First, let's see the effect of precession in electron diffraction. For a cubic mineral, first a conventional ED was collected, and then second ED diffraction data was collected with precession technique in the same orientation, and you can see two obvious things. First, more spots in higher angles where data was collected with beam precession, and second observations, there is an intensity variations in the collected diffraction pattern. Now, if we compare the precession electron data and conventional electron diffraction data with the kinematically simulated one, we can see electron diffraction data with beam precessions matches much more closely with the kinematically simulated data. In a second example, for cubic mineral nanite, electron diffraction data was collected with different precession angles. You can see by increasing precession angle, the intensity variations in the diffraction pattern shows up again. Hence, to summarize the benefits of using precession in electron diffractions are intensity variations in the diffraction stay like kinematical one, that helps in right symmetry determinations and the structure solution. Now, what is precession technique actually is? In precession electron diffraction technique, a tilted electron beam is rotated very fast around the central axis of the microscope, and subsequently, an electron diffraction pattern is formed by integrating over a collection of different diffraction orientation conditions. Nanomegas has designed a dedicated hardware to do beam precession, and it is compatible with all the electron microscope in the market. It is currently being used close to 200 labs in worldwide. What are the different steps to obtain a structure from 3D electron diffraction data? That's the interest of all the scientists or all the material scientists. First step is to do a sample preparations and align the TL for the diffraction experiment. Second step is to collect 3D electron data using the hardware developed by Nanomegas. That means you collect precession electron diffraction, 3D precession electron diffraction data. Third step is to determine unit cell symmetry, extract intensities from the collected 3D electron diffraction data. This can be done with a dedicated ADT3D software supported and provided by Nanomegas. Fourth step is to do structure solutions using structure solutions program like IANA or SID. This structure solution process can take between couple of hours or it may take many days based on the complexity of the structure. First and the last step is to do a kinematical refinement of the structure. In most of the cases, this is sufficient to solve a structural problem. And after that, then the refinement can be done using programs like IANA, Selex, or SID software. I will discuss each of these steps, especially step 1 and step 2 in the next few slides in more details. There are different standard and non-standard methods for sample preparations, as you can see. I am not going into the details as sample preparation can take hours and hours. Some of them are suitable for material science applications. Some of them are for pharmaceuticals and macromolecules applications. Instead of going through all the different sample preparations methods individually, I will show in the application examples which methods has been used for which type of materials analysis. But the most important point one need to keep in mind, the sample should be beam transparent for electron diffraction experiment. For PM settings, electron diffraction data can be acquired either in a STEM or TM mode. STEM mode with low temperature conditions are recommendable, especially when working with beam sensitive materials like pharmaceuticals or macromolecules, even for geolites or metal organic framework structures. Because STEM conditions allows lower electron dose on the sample. And regarding the sample holder, cryo sample holder can be used, especially with when working with beam sensitive materials, but otherwise single tilt holder can also be used. For unit cell determinations, a smaller tilt range is good enough to obtain reliable results, but for structural solutions, a higher tilt range is required. The required tilt range will depend on the symmetry of the material. Lower the symmetry, you need higher tilt range for solving a structure. In 2016, using direct electron detection camera for the first time, we solved organic structure of carbamazepine and nicotinic acid at room temperature. The result obtained by electron diffractions matches well with the result obtained from the single crystal data for these same materials. And this result was highlighted by International Union of Crystallography, as this is the first structure solved with electron diffraction at room temperature for an organic pharmaceutical. For more details, you can see the publication mentioned in the presentation. Now, to acquire 3D data, one has to first find the crystal in the TM grid, which is beam transparent and separated from other nearby crystals. Only then one can start collecting the data either by tilting the crystal in fixed step size, 1 degree or less, or otherwise with continuous rotation. The electron diffraction data are usually acquired with beam precision to obtain better quality data, which we always recommend. During the tilting, the crystals usually moves away from the beam because the all goniometer are not very stable once it goes away from goes to the higher tilt range. And in that case, you need to readjust the crystals manually to put it under the beam. Once the process is finished, a 3D electron diffraction data is acquired in electron microscope. The acquisitions process is highly reproducible, robust, but it take a couple of minutes or hours depending upon how challenging the sample. The technique of collecting 3D electron diffraction data was first proposed by Ute Kolb in 2007, and it is known as automated diffraction tomography. Since then, there have been different variants of the same methods proposed by different authors for collecting 3D electron diffraction data. One of them is collecting data by continuous rotation of the crystal. This was first proposed by Letadlov et al., who is currently working with the TM manufacturer, and subsequently Tamit Gonen and other scientists too. All of these techniques are variations of the same technique proposed in 2007, so we will call all of them as 3D electron diffractions throughout the presentations. You can see more details of acquiring 3D electron diffraction data and its terminology used by the different authors in the recent publications of ACS Central Science, as I have mentioned in this slide. As I said before, structure solutions by electron diffractions has really started from 1976, though it was originally started much before. In 2007, there was a special issue on structure solutions by electron diffractions, where Stavros was one of the editors, who is now a director of Nanomegas. Structure solutions by 3D electron diffractions and with beam precisions has been started from 2009, and all these years more than 150 structures have been solved. And also during all these years many types of structures have been solved. Some of them I will demonstrate it here. In all these years, some of the structures are known, some of the structures are unknown, some of the structures was also not possible to even solve by high quality synchrotron data sets, which was possible to do by 3D electron diffraction data. Now, one of the most important things which comes to the mind of all the scientists, how precise is the structure solved and refined by 3D electron diffraction. For this purpose, I have taken an example from our work on 3 different materials where structures were solved and refined using 3D electron diffraction data with beam precision. In the last column, you can see difference between the atomic coordinates of the solved structures by electron diffractions and structures solved by single crystal X-ray diffractions. And you can see that indeed it is possible to obtain structures of 10 picometer accuracy or 0.1 angstrom accuracy with 3D electron diffraction data. In the next few slides, I will show you 4 selected examples among many others where 3D electron diffraction technique has been applied. First one is a geolites example, which is a beam sensitive, relatively beam sensitive material, and where it was not possible to grow large crystals of single phase suitable for single crystal X-ray diffraction. Neither it was possible to extract structural informations from the powder diffraction data which was collected in the synchrotron beamline. In this case, 3D electron diffraction method was applied. Sample was prepared by gently crushing the material, and the data was collected from a small crystal, which you can see in the slides, with continuous rotations combining beam precision. From the obtained data, unit cell and symmetry was determined, and ultimately it was possible to solve the structures as well. And from the obtained structures, it was further refined against the powder diffraction data, which was collected from the synchrotron beamline. The data was acquired in 3 minutes to reduce the beam damage, and the work was published in JACS. And you can see more details of this in the 2016 publications of us. Second example is studying the nickel diffusions of a gallium arsenic nanowire by thermal annealing in nitrogen-rich temperature. First, EDX analysis was performed. From the chemical analysis, 2 different phases across the nanowire was observed. 3D electron diffraction data in stepwise mode with precision was collected from these 2 different locations where there was 2 different compositions was observed by EDX, and unit cell was determined. The obtained unit cell matches well with the X-ray result from the bulk material. By using the 3D electron diffraction data, it was also possible to solve the structure for both of these phases. In this case, electron diffraction data was acquired in stepwise mode as the crystal size was really small, and tracking the crystals under the nano beam was extremely challenging. I have referred back the paper here. This is not a work of us, but if you want to see more details, you can see it in the if you go to the publications more details. Third example, it comes from us, is studying a naturally occurring mineral zaccharinite. This mineral was first discovered in Dominican Republic, and it comes and aggregate with many other minerals. So it was not possible to do any structural analysis using X-ray diffraction method. But in 2012, it was possible synthetically grow the same materials in the lab, and the structure was proposed using X-ray diffraction method. In 2019, we studied the naturally occurring form of this mineral. Sample was prepared by FIB to get the area of interest. In the ADX analysis, we have seen a second phase in close proximity of the zaccharinite. 3D electron diffraction data was collected in stepwise mode with beam precision, and then subsequently unit cell was determined, and the structures was also solved, which matches with the X-ray diffraction result proposed in 2012. But we have some additional observations. We saw presence of modulations in the diffraction patterns, which was also confirmed by looking the HRTM image of this naturally occurring mineral, which actually was not possible to see in the synthetic form of this mineral. This result was published last year, 2019, in Microchemical Journal, and you can see more details in the publication. The last example is one of the really nice example which I like, studying the pigments responsible for the color in an early 5th century BC glass amphoris. The sample was excavated from south of Greece. First, we have done EDX and EPM analysis to find the chemical composition of the pigment. Except the usual component present in the silica glass, which is silicon oxide, we have seen traces of titanium oxide, cobalt oxide, and copper oxide. Then the sample was prepared for electron diffraction experiment by ion thinning, and 3D electron diffraction data was collected, and from the 3D electron diffraction data, a primitive hexagonal cell was obtained. Based on the obtained unit cell and the chemical analysis, we have looked into the structural database, especially from the ancient period, to understand what this phase is actually belongs to. There are two big blue pigments we can see in the literature. One is the Egyptian blue, other one is the millerite or sumurite mineral. As the structures what we got is hexagonal. First options we have discarded, and then we picked up the second option. Interestingly, the mineral which you observed in the same hexagonal phase mineral has also been found in a 1113 BC scarab of Egyptian origin in Sardinia, Italy. At the same period, the same mineral was found in Greece. Possibly there was a trade route between Egypt, Italy, and Greece in this period, and that can also be confirmed from the other literatures. We have studied several other pigments. You will find more details in these three publications. Now, in all these previous slides, structures have been solved and refined assuming the kinematical intensity of the diffraction data. And we have also seen one can get very accurate results close to 10 picometer accuracy with this refinement. But one can go a step further to improve the quality of the structures by doing dynamical refinement, which I will not be able to discuss or explain in more details due to the time constraint. But let's see an example where a mineral structures was refined kinematically and dynamically and compared with the X-ray result. One thing you can see visually is that there is a better agreement of the structures with dynamical refinement. Now let's see some numbers to understand the quality of the refinements. One thing you can see, the R value has dropped to the dynamical refinement. That means we got a better quality structures. Positions accuracy has also been increased with dynamical refinement. Also, there are many things one can do dynamical refinements, like analysis of the disorder, finding the hydrogen atom positions, absolute configuration determinations. But one need to keep in mind precision is really mandatory for doing any type of stable refinement process, be it kinematical or dynamical. The results you can see in more details in these three publications. There are more, but some of the most important one I have shown it here. Then what next? What are the future promises of this technique? In next few years, we believe structural analysis by 3D electron diffractions will have a major contribution, especially for in situ process, as now in situ sample holders for TMs are commercially available. And also solving structures for macromolecules will be more accessible. In the first example on the left, during the electrochemical process, a new phase was formed and subsequently lithium iron phosphate structures was solved by collecting 3D electron diffraction data in situ. From the macromolecules, this is one of the recent examples, is lysozyme structures which are solved by 3D electron diffraction data. More precisely with 3D electron diffraction data with beam precisions. With this, I'll finish the presentations related to 3D electron diffraction. And if there is any questions related to this topic, I'll be able to give the answer after the webinar in the question and answer sessions. Now the second part of the presentations, which is in this part of the presentations, I will show the electron pair distribution function technique and how it can be applied for characterizing amorphous and nanomaterials in a transmission electron microscope. Okay, so a crystalline material, a material in a solid form can either be well crystalline, or it can be a nanomaterial, or it could be an amorphous. Crystalline material shows sharp diffraction spots, or it can be seen, as you can see it in the left side of this slides. in a one-dimensional diffraction pattern. Once the particle size becomes smaller, the diffraction patterns becomes broader. And for an amorphous material, the diffraction patterns is very, very broad. So there is no direct way to extract any structural information for this type of material, for materials, for the nanomaterials or from an amorphous material. Transmission electron microscopy or scanning tunneling microscopes can image single atoms or columns of an atom. It can also reconstruct atomic coordinates from three-dimensional tomographic reconstructions from different sections, but it is far from routine, and also many things needs to be sorted out, like you will have a beam damage if you have a delicate samples. The positional accuracy is much lower than any other crystallographic methods. One approach to solve this problem is to use paired distribution function to extract structural information. In this method, high energy X-rays or neutrons or electrons are scattered off by a material and detected by a detector. Very much like conventional powder diffraction experiment, which most of have you seen in a X-ray lab.